Hello class, welcome to SciGame. Here we are another session for lecture number 5 of surface chemistry. Today we are going to deal with enzyme catalysis. In previous class we have already studied what is enzyme catalysis. What are enzymes? Enzymes are the complex organic compounds containing nitrogen produced by living plants and animals. These can break high molecular mass into low molecular mass compounds. So these can act as a catalyst, and have to study about mechanism of enzyme catalysis. Before starting enzyme catalysis, the mechanism before starting mechanism of enzyme catalysis, we have to study the reactions involving enzyme. First step is formation of enzyme substrate. E process through second step is decomposition of enzyme substrate complex to the product. Here ES tries to product. So first step is fast reaction and second step is the slow reaction. And for forward reaction, let's consider the rate constant will be K1, and for backward reaction consider K minus 1, K minus. And you have to note certain notification such as E naught S. So these are the notation to know. E is the free enzyme, the enzymes available for formation of enzyme substrate complex, that is free enzyme, and E naught is the total enzyme, S is substrate, and ES is enzyme substrate complex. So first step, enzyme reacts with the substrate to form enzyme substrate complex, and in the second step enzyme substrate complex undergoes decomposition to form product and enzyme. So slow step involves the rate constant that will be equal to K2. So we have to determine the rate, and rate depends upon rate of reaction. Here slow step is the rate determining step, so I can write here dP by dt is equal to K2 equation 1, and I have to calculate the concentration of enzyme substrate complex. Since the enzyme substrate complex are involved in first reaction for forward backward reaction and for second reaction, that means the enzyme substrate complex is involved in three reactions, that is E plus S is raised to Es will be equal to E plus, here it is K1 K minus each. So since this ES is involved in forward backward reaction and this is the forward reaction, that means three reactions are involved, so we can calculate the change in concentration of ES, that is dES by dt is equal to K1 by considering forward reaction K1 ES minus K minus 1 minus K2. It is the total change in concentration of enzyme substrate complex. So by applying SSA, I can write dES dt equal to 0. So this will tends to 0. So K1 ES minus K minus ES minus K2 ES to 0. Consider this is equation. We have free enzyme will be equal to, free enzyme will be equal to total enzyme we have taken minus enzyme utilized in complex formation. Enzyme utilized in complex. So for free enzyme I have the notation E and that will be equal to total enzyme E naught minus enzyme utilized in chemical formation, enzymes utilized in complex formation will be yes. So the value of E I can put in equation 1 and the equation will be K1 multiplied by E naught minus S concentration minus K minus 1 ES minus K2 ES will be equal to 0. By opening the bracket I can simply write K1 E naught of E naught minus, so there will be S. So K1 E naught S minus K1 ES to S minus K minus 1 ES minus K2 and it will be equal to, by taking all the negative term on that side, so I can simply write here K1 ES into S plus K minus 1 ES plus K2 ES equal to K1 E naught to, by taking common ES I can get Es 2 into K1 of S plus K minus 1 plus K2, and it will be equal to K1 naught so I have the equation that is Es equal to K1 naught S divided by K1S plus K minus 1, and this is the concentration of enzyme substrate complex. So our rate of reaction will be, this is our rate of reaction, this is our rate of reaction will be equal to K2 into Es. In terms of Es, I can put the value. So rate is equal to K1 K2 E naught S by K1 plus K minus K2, and this is our, this is the rate of the enzyme catalysis. And this reaction can be simplified if I divide the numerator and denominator by K1, then rate is equal to, if I dividing by this by K1 and this by K1, then the rate will be equal to K2 E naught S divided by, have remaining K minus 1 plus K2 divided by K1 plus K1S divided by K1 this is Km. This is the whole constant. I can write this as Km. So rate is equal to K2 E naught S divided by Km plus S. This is the so-called Michaelis Menten so you have to, I had the derivation for Michaelis Menten equation, and here Km is Michaelis Menten constant which have value Km is equal to K minus 1 plus K2 so this is Michaelis Menten equation. Further, the Michaelis Menten equation, this consider equation. Further, the Michaelis Menten equation can be simplified as follows. Let us consider when all the enzyme will gets reacted with the substrate, all the enzyme will react with the substrate, then concentration of E naught, that is total enzyme we have taken, that will be equal to formation of or concentration of enzyme substrate complex. So we have rate is equal to K2 into Es from equation 1. This is the equation 1. This is the yes, this is the equation 1. In terms of K2 Es, I can write K2 E naught. So simply write rate is equal to and this rate is the maximum rate. I can simply write R max equal to K2, or this R max is equal to K2 E naught, which also can be written E max. That means maximum velocity. This is the term or notation usually used in enzymology. So Michaelis equation now can be written as, this is the Michaelis-Menten equation, rate is equal to K2 E naught. In terms of K2 E naught, right, Vmax, the rate is equal to Vmax S divided by Km S. So here two cases arises, that will be case 1 case. What is case 1? For case 1, consider Km is very greater than, if Km is very greater than S, that means S is negligible as compared to Km. So I have rate is equal to Vmax by Km to S. Vmax by Km equal to, I can write this as another constant Vmax km. This Vmax by km I can write another constant, that is k dash. So when km is very greater than s, so I have rate is equal to k dash into s. This is first order. When the substrate concentration is very low, the enzyme catalysis follows first order reaction. Then again we have case 2, when substrate concentration very greater than km. If substrate concentration is very much greater than km, so I can neglect km. So km tends to 0. So rate is equal to Vmax s divided by s. So rate is equal to Vmax. When substrate concentration is very high, then enzyme catalysis follow 0 order. So rate is equal to their constant. So this is all about Michaelis-Menten equation. By using Michaelis-Menten equation, we can plot graph, which is also called Lineweaver work plot. So we have Michaelis-Menten equation, that will be equal to rate is equal to K2 E naught S divided by Km Km plus S. By taking reciprocal on both sides, I can write 1 by rate is equal to Km plus S divided by K2 E naught